Good afternoon. Good. So we're going to continue our discussion on sorts. Yesterday we covered bubble sort, and what you saw was that that's an order n squared sort. And even if we fix it up a little bit, the time it takes, it's still order n squared in the worst case. What we want to do is look at some other algorithms, and remember each time we want to compare back to bubble sort. For each of these, I won't necessarily show you the actual code. What I'll focus on in the lecture anyway is the mechanism. So I might describe using some pictures and diagrams, etc., how the data moves around, enough that we can do an analysis to get a time complexity and then do the comparison to bubble sort. The actual exercise of trying to code these I've left to some extent to explore, for you to explore in the tutorials. So, you know, it is, well, if you have further questions, of course, you're free to ask them. So the first sort that we're going to, in a sense, take seriously, so bubble sort is there as a reference. The first sort that you're sort of implicitly, intrinsically responsible for is insertion sort. So here's how insertion sort works. You're going to maintain, let me describe it first, and we'll write it down as an example. You're going to maintain two sections of your array. Think of it as the left side as the sorted side, and the right portion, or the rest of it, is your unsorted side. And on each pass, what you're going to do is take the first element from the unsorted set and find the right place to insert it within the sorted set. And so what you're going to have to do is just compare with each element, because they're, for argument's sake, as usual, we're going to assume it's sorted in ascending order, but this is not specific to being only ascending order. So what you're doing is looking for where that element that you've just removed from the unsorted set belongs. And because you're comparing to the rightmost element in the sorted set, then you're looking at the largest element you've seen among the sorted ones. So when you compare there, if what you're looking at is smaller, then it needs to move over to the left. So what you do is you swap. So that makes the largest element move over into the next, that region that used to be unsorted, that first one, and now you're still trying to find the correct location of that new element that you just inserted. So for that reason, it's called insertion sort, because you're trying to insert a new element among the sorted region on each pass. By the time you finish that, that means that at the end of the pass, the sorted region has grown by 1. Yeah? And therefore, if you continue that, you're going to eventually end up with a sorted set, because your sorted region increases by 1 each time. So by the time you finish all the elements, your entire set is sorted. How much time does it take to do a single pass? Well, the most expensive one, at worst, the last element you need to pick up needs to travel all the way back to the beginning, because maybe it was the smallest element. So that last pass could cost you order n. In general, the ith pass could cost you order I. So when you add up all these passes, you're doing it for n steps, n passes in total. How much does that cost you? N squared. Good. So worst case, that's order n squared. But your best case, order n. If it's already sorted, then each insertion step takes only a single step, and then you're done. Any questions? Oh, fantastic. I don't need to write anything. Let's move on. So that's the big picture. And on each pass, you're going to take an element. On pass I, you're going to insert element EI, which is the first of the unsorted part. So excuse me. To summarize what we just said, you need n passes in all, or n minus 1. The total cost for a single pass could be at worst order I time if you have to move past all I elements. And the number of passes is, let's say, n minus 1. So your total time is the sum from I equal 1 to n minus 1 of order I. And so that's going to give you order n squared. That's worst case. And your best case will be order n. Because each insertion, if it's already in sorted order, then it means that your sorted region starts out. You always assume that the first element, a single element by itself in a set is sorted, right? So that first element is already a sorted region. That's why you only need n minus 1 passes. If it's already sorted, then it means that the next element that you pick up, when you do your comparison, you're not going to need to move it. And so it takes order 1 time to do that comparison and leave it alone, and you're done with that pass. You move on to the next pass to move the next element from the unsorted region over. Any questions? All right, I'll take that as a no. There are no questions. All right. I thought you might want to see an example, but it's okay. So heap sort then. Question? I just switched it. Who's asking? Can you read this? Can you see it? Come closer. This is as dark as it gets. So if you can't see this, then I can't help you. This is all marker I have. That's of this dark. So if you can't read it because it's not big enough, that's a different story. I can try and draw the letters. But if it's not dark enough, I can't help it, because this is as dark as it gets. Which is it? Okay, then you need to come closer. Hush. All right. Heap sort then. I don't know what else to tell you. You're welcome to come stand up here, sir. All right. What happened? I think he said, oh, thought you figured out something. Okay. All right. So if that's clear enough, let me move on to the next sort. Sorry? There was, but there are no questions forthcoming, so it must be clear. And there's no need. Sorry? Oh, you need an example? Oh, okay. If you don't, it was so crystal clear. I thought there's no need. There's no need for it. Well, it costs time, and we never get time back. So. All right. So apply insertion sort to the following. you make me check off the topic and it don't finish. All right. So maybe I should use the same list we had yesterday. Remember it? Call it out for me, please. And 3. All right. So to begin with.
So do I know it? I don't know. Leech. I don't know Leech.
Table of questions?
Leech. Even worse, no. Alright, give her my congrats and stuff. Do you love freeness?
I don't know who this is. Okay. All right, so start with the partition. You would have yes? What color is that? Oh, black would be perfect. Thank you. Department is out of black, so thank you.
That's a gay song, by the way.
All right. So here is the sorted. I'll draw that black line to show the partition. Remember, to the left of that, it's sorted already. So the first step would be to pick up 15 and do the insertion, insert it in the correct place. But how does that work? That's a sequential comparison, one after the other. So in this case, we're going to do a comparison like so. And that's smaller, so that's going to move. In this case, it's only one step to move. So that's what it looks like by the time the first pass has ended. But remember now, we just picked up an element from here and inserted it, so the sorted region is now 2 elements big. When you insert the next one, this 40 you're going to compare with the 31, but it stays. So we'll do this comparison, but I won't put any arrows because they won't exchange. So next step, looks like that. Next one, you're going to compare 7. Now the 7 compares to the 40. That requires, it's less, so it's going to move. And then we're going to compare with the 31. And it's smaller, so it moves again. Compare with the 15, and it moves again. So at the end of our third pass, we'll have 7, 15, 31, 40, and 3. And of course, once again, pick up the last element, in this case the last element. So the next element from the unsorted region and perform a comparison. It's less than 40, so it needs to move again. Less than 31, less than 15. Compare with 7, it's less than. And so we're going to drop it in front. notice that what you're doing each time is in fact swapping the element. So if in fact 3 is less than 40, you're actually doing an exchange right here. So that moves the 40 preemptively. Why is it useful to do that? Well, you know, at some point, since this 3 is less than this 40, this 3 belongs in here somewhere. You have to make room for it anyway. So you're using the moment where you're doing the comparison to also do the move. And therefore, you save yourself an extra pass. Okay, so it's not the same as, for example, if you thought, maybe I'll just scan down, compare, and then when I find the right place, insert it in there. Because when you do that, then you have to slide everything up anyway. It's about the same total amount of time, but I don't know. If you're in a contest, that might make, you might save a millisecond or two. Microsecond or two. All right, so that's how it works. Any questions? Okay, heap sort. Now, heap sort, you could probably imagine what heap sort is, now that you know what a heap is. So let me just tell you off the top of my head, as in just a brief description, and let me see if you get it, just from that very brief description. So you know that your heap is good at organizing either the smallest or the largest element to be at the root of the tree, right? So if you rip off that, let's say we talk about minimizing heaps so far. If I remove that minimal element, that takes me how long? I don't want to remove it. I don't want to look at it. But if I take it out, it takes me log n to fix it back, right? Because you have to do that deletion and push the value down, etc. But when I take that minimum element out, I found it real quick, I removed it, log n time, I could store it in an array, don't it? And I just have my smallest element right there. How do I get the next smallest element? Just remove the minimum from the heap again, does it? Because I've already taken the least element out, so what's left is the second least element of the overall original list, but it's left as the minimum element of what's left in the heap, don't it? So how could I sort with this? Just keep repeating that process, don't it? So I'll get it out, minimum, then I'll get the smallest first, then the second smallest and the third smallest, etc. By the time I'm done, I'll have a sorted set. That's heap sort. Does it need any further discussion? There's only one. There, yes? Oh, you know. All right, you have a question? There's one useful caveat that will apply if we're now discussing how much space we might need to do this. Do you remember from the tutorial where we discussed how to implement a heap using an array? We talked about this embedding. So that is a very clever way of putting a tree inside of an array so that you didn't need to have linked lists or pointers or anything like that. It was a straight indexing into this array, and we could get at the elements of the tree. You remember that? And the basic formula was, the idea is just that if you have a node at index I, put its left child at 2i and its right child at 2i plus 1. Yeah? And that gives an embedding. Well, if you do the following, instead of a minimizing heap, if you use a maximizing heap, then you'll have the largest values at the root. And here's a neat trick. When you take it out of the heap, that heap is going to shrink, leaving space in that array at the end for you to put that maximum value in. So you see what just happened? So you have an array. Initially, it's supposed to sort. You call heapify on that array. So now you have a heap of the same elements occupying that same space as the array. Now what do? Pull out the maximum. So you do a delete max, because it's a maximizing heap now. And when you pull it out, the heap shrinks a little bit by one element. And that same space that it shrunk and left, you simply store that maximum value there. And if you keep repeating that, what will happen is the end result is that your final array is going to be sorted, but you took it out from largest value going down to the smallest value. And the neat thing there was that the heap would retract or contract at exactly the same rate that you needed space to put the elements that you've figured out where they belong. And so you could sort the whole thing without using any extra space. There's a special name for those things. Soon come to discussing that. But let me document what we just said. Well, if I need to. All right, so this one is going to be real brief. Given an array, we're going to heapify and repeatedly remove the maximum element That's going to happen. What's going to happen overall n times? Okay, what's the time complexity of this? Let's think about it a little bit. The time for each remove max is log n, right? And I did it n times. Why would you say log n squared? N log n, thank you. Whoever said log n squared was probably thinking that you're doing I work log n times, but that's not what's happening. You're essentially doing log n, at worst log n work n times. We've been through this, I think. What you really have here is a sum of logs. So you're doing log of 1 plus log of 2 plus log of 3 all the way up to log of n work. And what we've discussed is when you add that up, I think I discussed this in a tutorial, maybe in a lecture, can't remember exactly where. But if you think about that carefully, you realize, wait a minute, it's not actually equal to adding up log n times. But what we discussed was the order of growth is roughly the same. And for those of you who may not have caught it, consider what happens if you took half of the elements from log 1 up to log n. That would look proportional to log n over 2. It's at least log n over 2. And you have n over 2 elements like that. So that's certainly order n log n. And that's a low bound. Upper bound is n log n as well, because they're not more than log n each, and you have n of them. So low bounded and upper bounded by order n log n, that means theta n log n. Right. So the time for one delete max. And time for your heap sort. Now, when a sort doesn't use any extra space, then it's called in place. So when I say no extra space, meaning the amount of space beyond the size of the amount of space you need for the input. So not counting the space you need to store the input itself. how much more space do you need for the algorithm to run? That's the question being asked. If that space is constant, so if it's order 1 space that you need, then that algorithm is, or that sorting algorithm is said to be in place. So you can see where, based on how I describe this, heap sort is an in-place sorting algorithm. You did? So based on that, let me ask you now regarding the other 2 algorithms that we look at. Insertion sort, is it in place? Is it in place? Yes. So based on this, certainly I didn't use any extra space. How about bubble sort? Yes or no? Yes, I didn't use any extra space yesterday. Remember when you swapped elements, you know, you might need 1 temp, but I didn't need to allocate a new array or anything. We just moved the elements through that initial array. So far, of all the sorts we've looked at so far, all 3 are in place. So a bubble, insertion, okay. So far, which is the best sorting algorithm that we've looked at so far? Heap sort, good. So you're following what I'm saying. Because here you have n log n performance. So far up until now, the worst case we saw was n squared. So you might have been wondering at first whether there was any better way to do this. And actually, when you think about the fact that you can do it in n log n time, that's actually, if you think about it carefully, you realize that that's actually pretty amazing. Because n squared means you have to compare every element with every other element, roughly. And if you're doing a sort, you might imagine that that's unavoidable. The fact that you can do it in n log n time tells you, actually, you don't really need to do a comparison between every possible pair of elements. And that in and of itself is interesting. Why does that happen? It's a slightly philosophical question. How is it that we can get away with that? The short answer is that when you do comparisons, you get a little bit more information based on what other comparisons you've already done. Why? Because less than, or in general, our precedence operator is transitive. So for example, if I've compared A and B together, and I know A is less than B, and later on I compare B and C, and I know B is less than C, I don't actually need to compare A and C anymore. Right away I know that A is less than C already. So the point is, there's opportunities depending on the order in which you do the comparisons and depending on what you compare when, that you might be able to save some time and work by avoiding some unnecessary comparisons. Essentially, you have enough information to know that you don't necessarily need to do certain comparisons. And it's cleverness in using that or exploiting that opportunity that gives rise to this kind of running time. Now, it raises an interesting question, and while I present the next 3 algorithms over the course of the week, I want you to think about it. And the question is, so is it possible to do better than this? Might it be possible to go even faster than n log n? I'm going to see the answer to that eventually, probably by Monday. But let me press on with the next algorithm, unless there are any questions. No?
You have to pay a deposit by the end of this week in order to secure it. Because she said that she's not supposed to hold it for me. But it's because of the deposit? On campus. So I don't mind if you come on with it.
Okay, so here's the idea of merge sort.
Everything and it comes and it inclusive with water.
You're giving your set as usual. You have n elements in it. And this is how this one works. This one says
it's expensive because I'm living here.
Basically avoids doing a sort until the set is so small that it's easy. So if the set has only 1 or 2 elements, good. If it has only 1 element, fantastic, we're sorted. If it has 2 elements, do a comparison and swap if necessary. Then we're done. That makes sense? So far, so good? Okay, anything more than 2? It says, all right, that's too big to handle. What we're going to do is divide it in 2 and recursively sort each half. Sound like a plan? To divide any number enough by 2, divide any number by 2 enough times, you will get a value, a result that is less than or equal to 2. Yes? Right. So that will bottom out, certainly at those 2 simple cases, and then we'll have it sorted. So that sounds like sort of progress, but I still have one challenge though. I have lots and lots of tiny little pieces. Each of them are sorted, but they still need to come together to form one big array. Don't it? Okay, so the process then is given 2 sorted arrays. To put them together, what we want to do is, it's called a merge. So you want to perform a merge operation of the two sorted sets in such a way that the resulting set is sorted. Now that's easier to do than if you just had 2 arbitrarily organized arrays, because since you know that they're already sorted, I could start from the smallest end of each one and basically do a comparison of the 2. Whichever one is smaller, you move that into your result. And so you leave the reference to the other one where it was, and you advance the reference on the one that you just removed. What are you doing there? You see, the reason why that works is you're already looking at, when you just start, you're already looking at 2 smallest elements, right? When you remove one and put it in the result, and you advance that reference, you're looking at the next smallest element in that set. You know you don't need to look any deeper because all the ones behind it are bigger. And so when you compare that one with the one from the other set, whichever one of those 2 smaller must be the one that belongs next in the overall set of the merged result. So that process is called merge. So merge sort is essentially divide up your array, recursively divide the array into halves until it gets to the base case, in which case you can return it sorted. And once you've gotten the 2 sorted pieces, run merge on them. That's it. Any questions? Fantastic. So we're done? Well, you see, if you don't ask questions, that must mean total comprehension, right? I'm going to stop writing. I'm going to only write what you ask. Right? Answers to what you ask. Okay. All right. So, let me present the sketch of the algorithm, and then I'll show it on an example. That be enough? So, I'm writing it like it's Python code, but I'm gonna write it in pseudocode. So here's a comment: swap if necessary and return. And then comes the important part that makes it called merge sort. You're going to divide it in two. And then you're going to call sort. Which sort are we going to use? The same merge sort. So let me call it left. In Python, I can conveniently slice. So that's everything up to the midpoint, everything from the midpoint to the right. And then you're going to return. This is where the merge happens. Okay, so that's the gist of it. That's not more than the gist. That's actually it, except for this boring piece here. We're just taking up space and not been very valuable. So the only thing perhaps to explain a little bit, and I'll do it with an example, is how this merge looks when it runs. Does that correspond to what I described to you? Or did you have something completely different in mind when I finished my description? Or are you not connecting dots at all? You're just hearing one thing and seeing another, and maybe next week they'll connect. Or next month. So let me illustrate what merge would look like first. Since I'm not going to give you a code for merge, let me just illustrate how merge looks in general, and then I'll show you what the merge sort would look like when I'm running it on a small array. So as an example, suppose I had to merge those two lists. How this would work is you'd maintain two references or pointers, if you want to think of them, two indexes really, and they would be initialized to point like so. Then you'd be doing a comparison with those two elements. And compare this, move the smaller one down. That means you get to advance this one to now point at the next element. So now you're doing a comparison between the 3 and the 4. The smaller one down. So that's the 3. And you advance the one that you moved, right? So now this gets advanced to there. And you compare 4 and 8. Move the smaller one down. The 7 and the 8 get compared. Maybe what I should do is draw arcs to show which ones get compared. Because at the end of the day, you're just going to see some X's on those arrows. All right, so let's do that while I'm doing this. So here we go. Need a more distinct color. So we'd have done a comparison. There's another comparison here.
No.
And then we advanced the 1, so we did a comparison here. Can you see that?
Yeah.
And at this point, the 3 beat the 4. So we ended up comparing the 4 and the 8.
Yeah.
And then we ended up comparing the 7 and the 8. And that's where we were. Yes? So 7 beats the 8. So 7 comes down. That means you advance the pointer in that array that 7 came from. And that means now 8 and 11 are being compared. The 8 is smaller, so that's what comes down. Advance the 8, advance the reference. The 8 point at the 30, 11 versus 30. Means the 11 comes down. And once you're done with one list, you immediately just copy the rest of the other one down, because it's already inserted on. That clear? Why did I compare the 8 what? 3 times. How many times would you like to compare it? I mean, when you ask those questions, you make it sound like there's another number it should be. So I just wondered what you had in mind. I didn't know it was going to be 3. I just did what I was supposed to do. Were you not following what I was doing? Sorry? You just compare what? You did compare 7 with 8, and then you did what? 7 with 30, that's wrong. Because once you compare 7 with 8, 7 comes out, and you'd have advanced to 11. but you still haven't taken 8 out of the source list. So you have to keep comparing with 8. So you don't move on an element until you take it out. Why is that important? Because if you have a chunk, suppose as an argument, just by explanation, suppose this first element was something like 15, right? You guarantee that the one behind it is bigger than 15. Don't it? Because it's sorted already. So what would happen is you want to compare it. When you do this comparison and you keep advancing the other one, what would have happened is all these elements are smaller than 15. And so this wouldn't have moved at all. And you'd have ended up scanning the entire array and then essentially copying down the rest. Let me ask you now, how much time does it take? What's the time for a merge? At worst, it's the sum of the two. Maybe I should call that N1 and N2. You understand that notation, right? Those two vertical bars mean the size out or length out. Let's see how this would look. Oops, I rubbed off the array. Can you give back that array again? Yeah, or even today. All right. So first step, divide it in 2. Now if we divide it in 2, divide 5 by 2, one side gonna have 3, one side gonna have 2. You have to decide which side is which. According to what I wrote there, then that looks like, well, if you take that literally, it would look like I went to 2 and then I wouldn't even have scanned up to that. So maybe I should have added a +1 there. All right, fine. But what I would do here is typically, if you split that so that the 3 is on one side and the 2 is on the left side and the 2 is on the right side, that's fine. Just make sure you're consistent. Every time you split the odd number, if you make the left side bigger, that would continue to be true in every pass. All right. At this stage, this is small enough to sort. And so what this would do is produce a 15 and a 31. I'm going to put as if it's in its own subarray because it sort of is, at least the way it's written here. And then we would have then sorted the right side. That's too big. So we already started off making the left side smaller, which means that when I split this one, I need to split it there. Of course, the 40 can stay. It's sorted. The 7 and the 3, you'd swap. And then you'd merge these two. And when you merge them, you're going to end up with 3, 7, and 40. And then you'll be merging these two. And when you do that, you'll end up with 3, 7, 15, 31, 40. I'm going to leave it as a small exercise for you to, based on this code, do an analysis of this. And you'll get to use your, if you do it right, you get to use your master theorem, right? Can you see it?
Oh, wow.
Count the swaps and comparisons. When you do this analysis. If you want to count arithmetic operations too, that's fine. But can you see that in the recursive case, you have your recursive call, you have 2 recursive calls, and the size of each array is half of what you started with. So the size of these 2 are going to be n over 2 when your original one was n. And so your recurrence is going to look like 2t n over 2 plus constant. It's not constant. What's the overhead? This merge here is going to look like the other n total. There's 2 halves, n over 2 plus n over 2. So you're going to have a time complexity that looks like t of n, recurrence t of n is 2t over 2 plus other n. Use your master theorem, you get n log n. Okay, any questions? I'll see you on Friday. Oh, you guys know about, anybody interested in competitive programming? There's a movement afoot to try and get a critical mass of interested persons. And if it all goes well, maybe the best teams will get to go to the ACM and IEEE contest.
It's just a better choice. I didn't know that's what was